recording then. Hopefully that will work. Then, so welcome back. Yay, happy Thursday. Second to last Thursday ever in this class. We have our official countdown starting. So yesterday, shortly before the end of my workday, I sent out an email letting you know that I finally finished grading. So is that good news or bad news? I think it's good news. I think it's good news, yeah. So hopefully you were able to download your feedback from inside the homework portal and take a look at it. If you have questions, please let me help you. I don't expect you to read my mind. And I tried to articulate things in comments, but I may have not done a great job due to the sheer volume of them being provided. So if my expectations are unclear, please let me know and I will be happy to clarify them. Also, when you're doing your revisions, please use track changes. Please, I'm begging you. And leave my comments in so that I can see what I asked you to change. Revisions are optional. They are due at the end of finals week along with either homework 5, 6, or 7. It's the same homework with 3 different answer keys. So you just pick the software that you'd like to use and you can work on that. And the one last thing is formative assessment number 6. We get to talk about on Tuesday. I think you should be able to answer all the questions in it by now. That's my guess. Certainly the first 2, and I think the third one we talked about in enough detail, but today's example will hopefully reinforce it. So there we go. All right. Anything before we dive back in to talk about cross-random effects? And I'm sharing the screen, Zoomers. Don't worry, I didn't forget. No? We're ready to do this? Why not? So continuing with the mic drop lecture. What did we talk about last time? Do you remember? 2 days ago. What did we do? Erica, what did we do?
We talked about how everything is a multi-level model.
Everything is a multi-level model, yeah. That's the bigger picture. More specifically? Yeah, latent variables are random effects. So in the same way that you might be interested in measuring a latent trait, a latent ability, a latent characteristic of a person based on their observed item responses, we can use the models that you already know to do that because the latent trait is a random intercept for people. Beyond differences between people, though, in this type of design where we have multiple item responses collected from people, what else do we need to worry about? People get to differ from each other randomly, right? What else should? Items. Yeah, when is that relevant?
You have like multiple items that you're trying to like get measurements for. Like they might be related to a particular concept or trait or something. So like the reading passages, right?
Reading passages as a type of item?
They're all related to reading. They're trying to measure reading, but kids might get different reading passages that might have different inherent levels of difficulty that, as a researcher, you try to control for those things and make them as similar as possible. But
yes.
Unless you're testing for it, like it's a hypothesis whether or not they're actually similar.
Exactamundo. So if you have items that you're trying to use a lot of so that you have good reliability, but the items aren't exactly the same in terms of their difficulty, you can either try to make them the same and just like pray, or you can try to do something to control for it statistically. So whenever you have more than one item of the same kind and you have a question about whether they're exchangeable or not, that's relevant. And the items do not have their own properties in the model. That's the other piece of it. So if you're not putting in a fixed effect for which item is which, then there needs to probably be a random effect instead. That's what we were talking about. So do you want to see how to do this in software? See a little bit of examples? Why not? Why not? All right, so explanatory IRT models is what this is actually called at the same time. I call them multi-level models with crossed random effects for items and persons. 6 of one, half dozen of the other. So these are my dissertation data that I started talking about last time. Now that I know how to do it the right way, I'm going to show you how to do it the right way. And I did, by the way, look up, oh, I was going to show this to you too. Hang on. If Nikki is listening, you tell her this, she was right. It's the Dunning-Kruger effect.
Yes.
Yes, and after class, I Googled this and came up with all kinds of images, and there was one that I really, really liked. Let's see if I can find it again. Oh, I found it. Okay, I gotta open this. The Dunning-Kruger effect. Okay, so there's conviction on the y-axis and knowledge on the x-axis. And stage 1 is pretty damn sure you know a whole lot and feel great about it, which we call Child's Hill. That is accurate. Ask a 5-year-old if they're good at something. They are the best there ever was and the best there ever will be.
A 7-year-old, it works for 7-year-olds as well.
7-year-olds also very confident about their abilities. I believe Hugh, when he was 6, told me, I don't need to go to school anymore. I already learned everything. He might have a ways to go, such as how to spell more than his first name correctly. So Child's Hill here, and then there is a very sharp drop-off. I like the child is tumbling here, questioning whether you know that much, acknowledging that you don't know much, down to Insecure Canyon, which I think is where most of us live most of the time, right? It's like, I don't know much, but I know that I don't know that much, and I feel very bad and embarrassed about that. Ashamed. But then you get up to Grown Up Mountain. And the rest of the pictures that I saw with this had this nice, smooth curve, and I like that this one is wobbly, because that is quite accurate. There are peaks and valleys of where you realize you did get something right, and then you're like, oh, no, I didn't. Back to the drawing board. Realizing that knowing how little you know is the first step in becoming someone who actually knows stuff. So thank you to whoever made this. I enjoyed this quite a bit. So the Dunning-Kruger effect. I didn't know what I didn't know, but fortunately that article was only cited 22 times. So I don't think I did as much damage as I could have otherwise if I'd gotten something wrong on a larger scale. But anywho, we're going to get it right. So the story here, these are 155 older adults. I had more items than this, but I cut it down for the sake of demonstration to 36. I have whether or not they detected the change to the scene, so there's that flashing picture thingy, within 45 seconds or not. So most of the items were responded to accurately because that's a very long time to be staring at something. I also have a couple models at the end of this examining response time, just so that you have an example with a continuous outcome as well as a generalized outcome. I don't have any people predictors in the story today. I only have item predictors, but that doesn't mean I can't. We'll see how that could happen in just a bit. And I also wanted to note that not inside this handout, but inside the online materials are examples of how to actually fit these models using IRT functions in all 3 packages. So anyone who's planning on taking the IRT course, you're welcome. Here's a head start on how to do this stuff. So I did all of the data manipulation ahead of time because I got tired of doing it in 3 programs. So here are the variable labels for what we're going to be looking at. So I have person ID as a level 2 identifier, picture ID, which is going to play a couple different roles. Correct is my binary outcome variable. Response time in seconds is how long it took them within the 45 seconds, and it's missing if they did not get it correct. And then the 4 variables that pertain to the type of item it is, how cluttered the scene was, whether the change was relevant to driving, at how bright, how salient it was, and then whether the change was made to a sign. So clutter and brightness are on a z-score metric, the others are binary. So here are some descriptive statistics. 78% of the trials were responded to accurately overall. Response time, average of about 15 seconds. So this task actually does take quite a bit of time. Here's the same stuff within R as usual. And so first thing I'm going to do, single level empty model for a binary outcome. Why am I doing that? Why a single level model? So I have a comparison point and
to see what the model is predicting.
See what the hell the model is predicting. Yes. Especially useful in R because there is no decent documentation anywhere in R as far as I can tell. You can look up the documentation in other packages and get there the way they parameterized it directly, but this is also helpful to check. So here's how I would write the idea of predicting a binary outcome. This is the equation for what makes the logit. Logits are the log of the odds of the probability of a 1. I'm shortening it to that from here on out, and it has only a fixed intercept. And the subscripts I'm doing today are TPI for trial, person, and item. I don't have any trial predictors, but you could, so I left a subscript for those as a placeholder of sorts. So you've seen this before. I'm using ME logit and stata even though I don't have any random effects, just to stay consistent. In R, I'm using GLM within base R and the logit link. So then here is what I end up with. The fixed intercept, output just an R today. Sorry, stata folks, but it's in the thing. It looks all the same. You already know how to do this anyway. This is my intercept in logits, so 1.27. And if I take that and unlogit it, what's the technical name for that? If I go from logits back down to probabilities? Inverse link. Yeah, that's what you call when you go from model scaled back down to data scale generally. Within the logit link, the inverse link is e to the logit over 1 plus e to the logit, which I did the math right here, and came up with a result of 0.78, which should make me happy, right? Because 0.78 is the mean for this variable. So now I know it's predicting the 1 and not the 0. Yes?
Yes, quick question, Lisa. There I can see that your n is not the same for all your variables. So
That's correct.
Did you select complete cases?
This is the only variable that has fewer cases. It's response time, because if they got it wrong, I don't have a response time. And
Okay.
the model will end up only using the trials for which response time is observed when we use that as an outcome. But right now it's not in any of the analyses. We're just predicting accuracy instead.
Okay, great.
Yes, in this case, there were very, very rarely actual wrong answers. It's wrong because they didn't catch it in time. So it's actually a censored outcome. So now, random stuff. So for those of you who had binary level 1 predictors in your homework 4, this is how you would do your interclass correlation in empty models instead, our friend Glimmer. I'm using 1 point of quadrature, which is known as the Laplace method, in both of the packages. And I have a random intercept variance, 0.2. Is that a lot? I have even less of an idea, given that these are in logits, than I usually would. But I can test whether that's 0, right? Our friend likelihood ratio test. What I did here is use ANOVA to compare my single level model against my 2-level model, so providing a point of comparison, as you mentioned. And the chi-square test of 85, significant by either a standard or mixture chi-square distribution. Interclass correlation of 0.07. So these are trials to items that are nested within people. Okay, so this is a different context than what we've seen up to this point. Anyone want to take a stab at what this 0.07 is telling us? ICC is the proportion of variance that's between, right?
Persons
Between what? Persons?
in logit scale.
In logits, yes.
So,
And their response time
This is accuracy.
for accuracy.
So 7% of the variance in accuracy is because person-to-person differences. Or as you will call it next semester in your measurement courses, theta. Yeah. It's funny because the name of our program is Educational Measurement and Statistics.
mhm.
What's today's class? Which one is it?
Education?
Measuristics?
Ooh,
Statisment?
Exactly.
like measuristics. Can I make that a thing?
We should, on the registrar, let's do it.
Yeah, that sounds like an app or something. I used measuristics and it was amazing. But yeah, 7% of the differences are due to differences in people's ability to answer these items correctly. Person mean differences in this context. So the idea that ICC tells you the proportion of variance that's between, that is always true. It is up to you to figure out between what based on the context of the design and the sampling. So these are item responses, individual trial responses to different items nested within people. So 7% of the variance in accuracy has to do with which person is answering the question. So this is a standard 2-level nested model. Maybe we can call that statistics. The next one has a special name. I'm still keeping random people only, but now I am controlling for which item is which as a series of fixed effects by putting in picture ID as a categorical predictor. So note the notation. I showed you an example of this last time as well. I have commas in here because I'm going to have 36 of these, one for each item. There is no general intercept in this model. I kicked it out. Why would I do that? Because I wanted each of these fixed effects directly to give me the expected logit accuracy for that picture. If I had had a general intercept, each of these would give me the difference of that picture relative to a reference picture, and that is less useful. So I have the first item predictor is whether it's picture 1, the second is whether it's picture 2, all the way up to picture 36, which I lost somehow this. No, pick 36. There we go. Keeping the random intercept here. So this is a multi-level model in which I am controlling for which picture is which via fixed effects. That perfectly explains all the differences on average between items as to why some items would be more difficult or less difficult. The fact that these are being added together means these individual item-specific means are easiness parameters, not difficulty. The higher the value, the higher the accuracy for that picture. This model also has a special name. It is known as a Roche model. That is named after a person. Roche models are a family of psychometric models in which the common part that makes it Roche is that it assumes that all items are equally good at measuring the latent variable. They can differ in difficulty, but they do not differ in the extent to which they are predicted by the trait. So how do I do this? In Stata, I've changed a couple things relative to what you typically see. First is no constant right here. That kicks out the general intercept. And then IBN, I had to do a little bit of digging to figure this out. That means treat it as categorical, so I dot, but don't have a reference category. No baseline, I think, or baseline no. I'm not sure why it's BN, but who cares? I made it work. Still have a random effect of persons here. Likewise, in R, I kicked out the general intercept by putting a 0 there after the squiggle for predicting correct, and then picture ID is as factor. So even though this is one word, how many new parameters have I added?
36.
36. That's why my equation has to look like this. I have not just added picture ID, I've added all this stuff. So then, here's the solution. These are the means per item in logits. So picture 2, fairly low in accuracy. Picture 10, fairly high. And I have the labels out here trying to help us. Person variance is now 0.36 relative to the previous model, in which it was only 0.25. That strike anyone as weird? Explaining why some items are more difficult than others via fixed effects increased the amount of variability across people at level 2. Consequence or coincidence?
Oh, yeah, that's a consequence.
Consequence of what?
That we have fixed residual variance. And
Fixed
we're
residual
introducing
variance.
things
What's my e-variance in this model for binary accuracy?
30.29.
Yeah, the pi squared over 3, which is 3.29. What was it before? 3.29. What is it now? 3.29. The rest of the model has to increase in variance to make it so that there's still 3.29 left over. Coles, yep. They changed the regular price so that the sale price can remain the same, and it's just a bigger discount. Now it's 75% off instead of just 50% off. Yep. So this is where pseudo R-square gets weird in these models. It's not very useful, except in very few circumstances in which you can keep everything on the same scale. And R did not like this model. It had 0 level of okayness with this model, and I don't know why, because the other programs were like, fine with me. Now this set of 36 fixed effects is creating a more complex model than the model where I had a single intercept. So I could test whether there are significant item differences a couple different ways. One way is with a multivariate wall test, where I would lump together differences across, it'd be 35 differences for the 36 items. The way that it was easier to do in this context is a likelihood ratio test. So I can compare the previous model, in which I had one single fixed intercept, assuming that all the items were equally easy, against this model in which each item gets its own fixed intercept. And I'm allowed to do that because I'm using regular flavor maximum likelihood. We have never once done this semester, compared models that differ in fixed effects using likelihood ratio tests, because that breaks the rules if you're in REML. Cough, cough, homework 4 question. The ChatGPT folks. Mm-hmm. You're like, oh, that's what she meant. Yeah. So you cannot compare models that differ in fixed effects using likelihood ratio anything if you're in REML, but you can if you're in ML. This is ML. So I can do it this way. So my chi-square of like 700 says, yep, these items vary in their easiness. So this is helpful if I am really, really invested in each picture, right? If I had a research question about what happened with picture 23, this is the answer. But can I use this model to answer questions about why some items are easier than others? Shaking your head no? Why not?
I don't know, but I'm assuming
The answer is no. But why?
I mean, like, just generally demonstrating that there are differences doesn't tell you anything about, like, why those differences exist. Like,
Mhm.
you need additional information and, like, hypotheses about, like, why you think they might be, like, why you might have observed those differences.
Yes, I don't have any idea as to why picture 23 is much higher in accuracy than picture 2.
It's not in the model.
It's not in the model. It can't go in the model. So this model saturates, that's the word that I would use. It saturates all item mean differences by putting in which item is which as a predictor. But it doesn't help me explain why there are these differences. If I want to explain these differences, I need the same idea, I need the capacity to say that each item needs its own, but then reduce that variability. You know where I'm headed? So these are fixed effects of differences in item easiness. Can I do it a different way?
Random effect.
Random. Yeah. So what if I did that instead? And I just did. Our new friend, U, with an I at the end of it. This is model 4. So these are all empty models from the perspective of having any meaningful predictors. But this is now what I would call a crossed random effects model, because what I have are level 1 trials nested in level 2 people, also simultaneously but separately nested in level 2 items. Items and people are crossed random effects at level 2, in the same way that we would have kids nested in schools and kids nested in neighborhoods, and those are crossed. Remember that? That's this. Same thing, different context. So U is the random version of allowing each item to have its own easiness. But I'm doing it in the model for the variance instead so that I can predict why it is some items are easier than others. Not whether it's item 2 or item 26, but whether that item is relevant to driving or not relevant, or changes due to a sign or not due to a sign. Things that would predict difficulty. So this is the basis of a field of psychometric models that are known as explanatory item response models. Because if you have variability across persons and you have variability across items, then you have the capacity to see how much of each source of variability is reduced by predictors of that kind. Can you think of people things that might be related to differential accuracy?
Age.
Age, driving experience, whether you give a shit and want to do this or not. Like, there's got to be some sort of motivation factor here.
Could be like type of vehicle, novelty of it.
Sure. What kind of car you drive, how often you drive, stuff like that. All of those people characteristics could explain why some people are better at this task than others. Characteristics of the items can explain why some items are easier than others. So if we're going back to kids reading passages, the number of words in the passage, the difficulty of the vocabulary in the passage. Is it a story about like trucks, or is it a story about, war? I don't know. The context, right? It's making shit up. So this is both a multi-level model with crossed random effects, and it is a explanatory item response model, and it is also known as G theory. Some of you taking that class next semester, this is that.
Like the intelligence G?
Different G.
Okay.
Generalizability theory, not Spearman's G, like common intellect thing. Yeah, there's only 26 letters, so we keep reusing them. And yeah, in this class, ICC is intra-class correlation. In the IRT class, it's item characteristic curve. So there's all kinds of overlap of shared things that mean different things. But anywho, the difference is that G-theory models, from what I have seen, at least the older ones, do not have the link function. So if you see that, you should be suspicious, because you can't predict a binary outcome without a link function. Or you shouldn't, at least. It'll let you, but not a great idea. So to fit this, then we have to do the weird all R dot thing in Stata that we had to do before. And I put picture ID on this version of it because it only had 36, whereas I have 155 people, and it's supposed to be more efficient estimation if you make the smaller dimension the one that does it this way. So each item gets a random intercept deviation in this model. And in R, it's even simpler. It looks just like any other set of random effects, just different sets of parentheses. One for people, one for items. So now we have a variance across pictures rather than separate intercept estimates per picture. So it's a random intercept variance across pictures, not 36 separate means. In terms of intra-class correlations, the amount of people variance is about the same. It was about 0.07 before. It's about the same, 0.07 now. Differences across pictures, though, are larger. So 20% of the variance in accuracy has to do with which picture you're answering. And that is significant. Okay, how are we doing? Not bad. So in this design, each person saw each item one time. Therefore, the interaction of person by item is the residual, what I'm calling trial.
Can you repeat that again?
Yep. In this design, each person saw each item only once. So if you think about the random part of the model in a factorial ANOVA kind of way, this is a main effective person. This is a main effective item. E, if it were here, would be their interaction. So what is it about that person in that trial that made their answer different than would be expected just based on which person and which item it was? I don't know. I can't know because that's residual variance that can't be separated from the interaction term. But what if each person saw each item 5 times? Could I do that? In this context, it would not make a lot of sense because they'd probably remember the change and it wouldn't be the same item. But in other contexts, you might have people respond to the same item multiple times. In that case, could I have a subject by item interaction?
Yeah.
I could. So in the example that we did, example 5, we had students nested in primary schools and students nested in secondary schools, and they were crossed at level 2. And there were several instances in which more than one student attended the same unique combination of the 2 schools. Remember this? Maybe? And what did we add to the model to get at that unique combination and whether there was an extra correlation among the kids who went through the same school in both times?
Random effects interaction.
It was a random interaction term. That's a thing. So in this design, if I had each person respond to each item 5 times, then I could also add a U for the unique combination of that person to that item. Because I have 5 instances of it, I can pull that out from error. And what if I had them answer each item 5 times every day for a month?
You could model that too.
Yeah, now we pick up a random effective occasion. We could have person by occasion. We could have item by occasion. We could have person by item by occasion. Like, you can keep stacking these things up. That's generalizability theory. It's the idea that you are distinguishing different sources of variability due to different dimensions of sampling. And you can figure out how much of the variance is due to each and get indices of reliability and agreement.
So that'd be like in clinic doing like based on task, therapist, room, day of the week, what they had for lunch.
That's probably a fixed effect, but yes.
Well, okay.
Yeah.
But,
Yeah,
But you can like, I don't know, control is the control.
Control is a word I could use, yeah. I mean, this is controlling for item differences as a random effect, and the previous model was too. The difference is that when you make it a fixed effect, you can't do anything else to say why it is the way it is. If it's a random effect, that's a variance you can explain with predictors to say why it is the way it is.
Should probably be doing more of that.
More of that?
Well, yeah, because there's a lot of stuff that goes on. And
There's a lot of stuff. Yeah, so this allows you to test hypotheses about why it is. Some people are faster, some items are easier, some days are easier. You know, anything that you have that's information about that dimension of sampling explains that corresponding dimension of variance. Everything is a multi-level model, people. It is. It really is. So yeah, 20% of it has to do with which item is which. Significantly. So let's see why. I'm going to throw in my 4 predictors. So clutter, relevant to driving, brightness as another continuous predictor, and whether the change was made to a legible sign. Those go in the model as fixed effects, the same as usual. So there are 3 piles of variance in this model. There's E, which is not here because it's 3.29. There's people variance and their item variance. Which one of these is going to go down?
And then the item.
Item variance, because these are item things.
Predictors.
How much power do I have to detect these fixed effects of item things? Not much. The answer is not much. How do you know that?
There's only 36.
There's 36.
Wasn't there only 36 pictures though?
36 pictures.
But, I guess those were the only items you had. Never mind.
I got 36 pictures. I'm examining 4 characteristics of them to see to what extent differences across the 36 are attributable to these things, but 36 is not a lot. How much power would I have to detect why some people are faster or more accurate in this case than others? 155's worth. That's how many people I have. How much power do I have to detect trial level things, like whether the trial was first or last or something like that?
Well, each item is a trial, right? So 36.
More than that. 36 for one person.
Oh, 36 times.
The 5,400.
Yeah, I'm not doing that math in my head. But I'm going to go back up to the table where I know the answer. So this is the number of trials, 5,000 and some odd. Is this how much power I have, though? No.
I don't understand power, so this whole conversation is lost on me. Like I get like in like a big metaphor, if I have like a magnet, like I get that. That's about as far as I'm going.
Where I'm going with this is your chances of finding an effect that should be found, which is how I define power in a loose sense, increase with the sample size. And they increase with the size of the effect to be found. So the more units you have, the better your chances of finding something significant. So the point I was trying to make is 36 is not a lot. If I really wanted to make sure that my experiment were adequately powered for my design, those features, do I need to get more people? Do I need to get more items? Yes, I do. Yes.
This kind of goes into the design penalty and effective sample size.
Yes, that's where I'm going with the 5,000. It's not 5,000, right? How much is it? Not that, less. Less. Remember there was a formula, the design effect? The design effect is the penalty factor, and it's your intraclass correlation times the level 1 sample size plus 1, I think, something like that. I didn't do the math because I didn't do the math, but I'll tell you, your power is not 5,000. Your power is 5,000 divided by your design effect. That's your effective sample size that's powering this. So I have maximum power, relatively speaking, for trial things. Then next would be people things, and next would be item things. And do you remember my story about Larry, my friend from grad school? His F1 ANOVA was significant for his analysis because he went and got a whole bunch of psychology undergrads to do his experiment because they all got class credit for doing that. That's how all psychology experiments are adequately powered, as undergraduates against their will. Oh, they get to write a paper instead if they want, but no one picks that. But his F2 is not significant, which was the item level analyses, because he only had like 12 items or something. It's like, well, duh. I mean, you're interested in item effects, but you only have 12 items. You can't like fix that by going and getting more undergraduates. It's not going to work. And I have explained this in a couple different classes and watched people go, like, I'm never going to graduate now. Like, I can't get more items. There's only 12 words in the entire English language that meet these characteristics. Because they have to control for everything. So, If you're in that situation, I'm sorry, but you need more items. Okay. And don't feel bad about not understanding power. Like, power analyses are creative writing. I swear to God they are. Like whenever you see things, it's like, power is exactly 0.87. It's like, no, it's not. In order to know power, you have to be able to reasonably expect what to find for every single parameter in a model. And that is very difficult to do, especially if you've never done the study before. Okay, so we're going to try anyway, though, with my 36 pictures. And here's the result that I showed you in the PowerPoint. The only attribute that is significant is if the change was made to a legible sign. The logit of the predicted accuracy is higher by 0.74. And as anticipated, if I do pseudo R-square, my people variance stayed exactly the same. Coincidence or consequence? Consequence. Did I put any people things in my model? No. So why would it move? Did I put item things in my model? Yes, I did. It's 4 of them. And they explain 25% of the variance.
25% of that 0.07?
0.2, but yes. So the people variance was 0.07. The item variance was 0.2. So yes, I have 25% of the 0.2. That's what I have. Is that enough? Said differently, are there any other remaining differences between items, or are they more or less exchangeable now? Like all items of the same kind are exchangeable. If that were the case, then we wouldn't need the random item intercept. So I'm going to take it out, just put the random people intercept in, and do a likelihood ratio test. And the difference is 400. So if you take something away from your model and the difference in fit is significant, what does that mean? Did you make it better or worse?
Worse.
Worse. So interpreting likelihood ratio tests, if you added parameters and the result is significant, the model that you added it to is better. If you took parameters away and the difference is significant, then you made it worse. This is a made it worse kind. And everything is significant. So I would come to a very different conclusion if I looked at this without the random item intercept. For demonstrating purposes, I did some computations in SAS. So I have 4 different variables that I created at an item level data set. So I have a model where predicted from model 6. So I created predicted item easiness based on these features as a linear combination. I did that from the previous model, adding in the that had the random item intercept. I also created I had not predicted but actual item easiness from the Roche model, where items were fixed effects. That's the 3rd one. And then I did it from the crossed random effect model using the random effects instead. So the first 2 are predictions using only the 4 features. And they differ only in whether the model has a random intercept left over. The last 2 are not predictions using item features. They are the right answer. They are what is the easiness of that item if I treat it as a fixed effect or if I let all of the variance be part of the random effect. And if you look at the results of how related they are, the Roche model and the crossed random effect intercept model, both, they agree perfectly. So whether you treat items as a fixed effect or as a random effect, pretty much the same answer with respect to which ones are more difficult. Whether I have random variance left over in item difficulty doesn't matter. In terms of estimating the fixed effects, those are pretty much the same thing too. But if I compare the predicted to the actual, either within a fixed effects framework or a random effects framework, I get a correlation of about 0.5, which would be an R-square of about 0.25. That is exactly what I got out of the model as the R-square. So the predicted difficulty part, like in graduate school, this is how I learned to judge it. Is this sort of weird post hoc, take the Roche model estimates as the right answer, and then predict what the item difficulty would be from your features, and then see how close they are and say, yay, I got 25% of the variance. So the effect size for how well my item features work is the same, no matter how I do it, but my assessment of the significance of those features is very different. In the model that doesn't have random item variance left over, everything is significant. In the model where it does, only the last one was. And the fact that I need random item variance left over means that I should not trust this model. And what I did was wrong. Question?
Yeah, so when you were mentioning the Roche model and you said the right answers, was that because you were modeling accuracy, or do you mean like that is the correct answer to model?
Yes, thank you for the comment. I mean that it is the best estimate as to what the accuracy for each item could be, because in the Roche model, each item gets its own fixed intercept for easiness. So there's no misprediction that could occur. Okay, other questions or parts you want to hear again? So what else could I do with this? Well, I've got item things. Could I put in people things? Sure I could. Which variant should they explain? People variance at level 2. Could I put in trial things? Yeah. Like whether they had eaten breakfast that day or not, or I don't know, before that trial, or I don't know. Trial things, not people things. That would explain level 1 variance. What about random slopes? Could I do that? I just did. But over what is the question? What if I wanted to see whether people differentially benefited from how bright the change is? Like maybe somebody whose eyes don't work very well gets more of a boost from a change that takes up more pixels? Yeah? So could I have a random slope for the effect of brightness? How much that matters differentially? What is it random over is the question then.
Over people?
Over people. Now, what level is brightness as a predictor?
Level 2?
It's level 2. So we got level 1 trials, nested in level 2 people, nested in level 2 items. People and items are crossed at level 2. So brightness is attached to my right finger. It's an item thing. Its slope can vary randomly over people, the other level 2 dimension. We have not seen this yet. But if you think about it, if you're deliberately introducing things that make your items more or less difficult, it's reasonable to expect that people might be differentially susceptible to those manipulations. That's a random slope. But it's a random slope of a level 2 predictor over the other level 2 random dimension. That's my multi-level model explanation. I'm going to put on my psychometrician hat now and go back to measurement models. This is a multidimensional IRT model. I have 2 different kinds of thetas now. I have how good are you sort of on average in general, and then how much better do you get than other people if the change is brighter. Two different ways that people differ from each other, two different kinds of latent traits or latent constructs being examined. And why did I pick brightness? Because none of the other models converged. That's why. So I added brightness as a random slope after people, because it's an item thing, so it varies over people. And here, survey says, nope, no evidence of it being significant. But if it were, if I kept it, what kinds of variables would explain this random slope variance? That one. Your choices are people things, item things, or trial things.
People things?
You get 1 vote for people things, 2 votes for people, 3? Sure? People things, Zoomers, we're taking a poll here. The question is, the random slope for brightness, differential benefits of a change being brighter than another change. What kind of predictors explain that random slope variance? The room so far has agreed on people things. Got people and trials offered by the Zoomers. No one's picking items, though. The answer? People things. What makes a person differentially benefiting from brightness? Bad eyesight? I don't know. Age? Whether they wear glasses? Whether they had LASIK? I had LASIK, and it makes it so that at night the headlights are really dispersed, like they just go everywhere. So night driving is challenging. So yeah, people things. Could I have a random slope of a person predictor over items? I could. It breaks my brain to try and come up with an example, but it is technically possible. What about trial predictors? Like if I just literally put in a slope for which trial it is, but I log transform that variable so that the slope I'm creating is sort of exponentially, kind of levels off like that. Could I have a random slope of that? Like the extent to which you benefit from practice, we'll call it that. Sure. Do you think people benefit differently from practice?
Yeah.
Sure. Is that a people slope or an item slope?
People.
People slope. What kind of predictors would explain that?
People.
People things. These models get real complex real quick, but if you just hang on to the principle, like what is this variance over? Is it over people or is it over items? That's your answer. If it's over people, it has to be people things. If it's over items, it has to be item things. Yeah. Switching gears, that's what we were doing. So this was all accuracy, which means that we needed a link function and an alternative conditional distribution. What about response time? Could I predict that instead? I just did. This doesn't get a special name. This is no longer an IRT model. I know. It's still explanatory. It's like the same thing, but it just doesn't have any special names. So this is a multi-level model. This is not a psychometric model anymore. I didn't make up the names. But I wanted to show you just a couple because it works the exact same way. So if I start with random persons only, just like I did before, E is back. E can be whatever it wants because I'm using a normal conditional distribution. If I don't have a link function, is there a special name for that? It's general. What is the lack of a link function called as a name of a link function? Identity, yes. So these models are technically generalized models if you say you're using an identity link and you are using a normal conditional distribution. Identity link, seriously. I'm not making that up. That's what they call it. So yeah, I don't need to. This response time has a mean of 15 seconds, so I'm not worried about predicted values going below 0. It's not going to be anywhere near that. But if I were, then a different choice might be gamma or log normal for the distribution, and potentially a log link to make sure that everything stays positive. So if I look at response time instead, interclass correlation from an empty model is only 0.03. So very little difference across people in how fast they can do this task. But it is significant. I throw in my U for items to make it what I would call a crossed random effects model. And that results in quite a bit of variance. So people variance is up to 4%, picture variance is now 13%, and they're both significant. If I look at my item predictors, clutter, relevance, brightness, and whether the change was made to a sign, I've got my 3 piles of variance here. Which one do my item predictors explain? Which of these 3 should go down? So these are all 4 of these are item predictors. Item variance goes down. Yep. And in terms of our conclusions, 17 is the average response time for a picture of average clutter that's not relevant to driving, that's not made to a sign, and that has average brightness. If I look at the ones that are significant, for every unit increase in brightness, which is a standard deviation on the scale of this variable, response time goes down. So I'd probably say people are faster, is how I would phrase a negative slope in this context. So by about 5 seconds. If the change was made to a sign, they see it about 3 seconds faster. And both of those are significant. The amount of variance explained, 38% of the item variance. The others did not change as expected. Significant item variance remains, so we should keep it in the model in evaluating the effects of item predictors. How about random slopes? Could I do that too? Sure I could. So random slope for brightness, because why not? Survey says, nope, not significant. So now this model has 1, 2, 3, 4 piles of variance and 1 correlation. So this is one chunk. Person, as a level 2 unit, has an intercept and it has a brightness slope. That means that it gets a correlation between those 2 random effects that belong to people. The random intercept for item does not have any correlations that go with it, because that's separate. That's over here in this hand. This is the people hand and this is the item hand, and they don't shake hands. If I had a random slope of a person predictor across items, then that random slope would have a correlation with this random intercept. And then residual variance at the bottom is the lion's share of it. So why did somebody respond faster to this particular item, even after we control for which item it was and which person it was? Trial level variance. And then words. Ta-da! We did it. So connections in terms of other stuff that is here that could be here that isn't. This one, which one do I want? Let me go back to this one, Model 5 for a second. So IRT folks, this model assumes equal discrimination across items, meaning the slope that relates the trait to the item response. But there are extensions of these models that are not possible to do in this kind of software that do not have that restriction. You can have discrimination slopes that vary across items as fixed effects or as random effects. So that's something that isn't possible in here, but it is possible if you can get it to be estimated in software. Why is it that some items work better than others? That's a whole separate question. Why are some items more related to the trait than others? What features of those items control that? You could predict that as another kind of random effect. So it's a random slope of a random slope. And that's where my brain starts to break. But I think these connections are pretty cool. So I'm happy to talk with folks if they're interested in knowing more. But I wanted you to have seen it, okay? That's all. Just have seen it. All right. Questions? Comments? Did I blow your minds? A little bit.
Broken.
Is broken?
The same?
Yeah, I think so. Let me blow your mind. Do. I have that song in my head now. Gwen Stefani? No? Ask the Google. You'll find out later. So what is left then next week? A little bit about multivariate, a little bit about three-level models. Nothing about power, because you can read about that. If you ever need to do a power analysis, I can send you resources. I don't know how to do simulation for power very well in other programs besides SAS and M+, but I can certainly do those. All right. 137. I think I've sufficiently made it so we're not starting this today. Can we agree on that?
Mhm.
That fair? Yeah, okay. Okay then. So, recapping all the things that are on your plate and not on mine. Yay! I have to make one more example. That is what I have to do. Over the weekend, if you haven't done it already, please finish formative assessment number 6 by Monday night. We'll talk about that Tuesday. You can start working on revisions to homework 4 if you wish, and then you can start on 5/6/7 over binary models. Office hours as usual for everyone next week. And we'll reconvene for our last garbage day together.
Formative assessment 7 is about explanatory IRT.
Say that again?
The formative assessment is about explanatory IRT.
I had one question about it.
And the other 2 are about next things?
No, they were
or-
about things we've already,
past?
about generalized models.
Great.
Stuff we've already covered.
Yeah, great.
Yeah.
Thank you.
Yeah, I didn't think we'd get to multivariate this week, so I didn't put any questions on there
Awesome.
about that. Yep. All right. Katie made it to Sioux Falls. Woohoo! All right, thanks, Zoomers, for being here. I'll see you next week. Let me know if you need anything.